welcome back. This is Elementary Algebra. I am your instructor, Amy Fuchsteiner. I am a little bit of a mess at the moment. I changed my shirt into my favorite Harry Potter sweatshirt and was having some technical difficulties, but we are all set. And we're about to start section 5.2, which is exponents. Specifically, we're going to be looking at what happens when the exponent is a 0 and when the exponents are negative numbers. All right, so a 0 exponent. What does it mean when you have a 0 exponent? Well, part of the problem is that it doesn't mean what you think it means. The 0 exponents, well, let me try and explain the patterning to you, right? So if you have, let's say you have 5 to the 3rd power. This is 5 times 5 times 5. Or, what are we doing? Or 3 factors of 5. Let's go. There we go. 5 to the 3rd power is 5 times 5 times 5, or 3 factors of 5. 5 to the 2nd power is 5 times 5, or 2 factors of 5. 5, which is 5 to the 1st power, is the same as just a normal 5. If you have 5 to the 0 power, that's 1. Any base to the 0 power is 1. Okay, that base to the 0 power can be replaced by the concept or the number 1. This actually comes from wanting to keep the division or the quotient rule intact. So if I had, let's say, 5 to the 4th power, and I was dividing it by 5 to the 4th power, if I'm using the quotient rule, which I introduced you to last time, that should give you 5 to the 4 minus 4, or 5 to the 0. But if we look at 5 to the 4th over 5 to the 4th, this is the number 625 divided by 625. And we know anything over itself has to be a 1. So if I want to keep the quotient rule intact, if I want to make it applicable and the same, if I want to maintain consistency, that's the word I was looking for, consistency. If I want to maintain consistency, I have to let anything to the 0 power, 5 to the 0 power, be the same as 1. These are equal. I can tell you that once I learned this, I looked for 0 powers everywhere. I looked for 0 powers everywhere because it makes working with these polynomials and these monomials so much easier. For example, here I have 30 to the 0 power. This 30 is the base. 30 taken to the 0 power. Anything to the 0 power is 1. This is 1. This is 1. 30 to the 0 power is 1. Any base to the 0 power is 1. It is important to recognize what the base is. If we look at number 2, here you see 5y to the 0 power. Recognize the exponential and the base. The base is y, 0 power. So this becomes 5 times 1, which is 5. The y to the 0 power is the part that becomes 1, not the 5. The 5 stays 5. It was raised to the 1st power. That's not a 0 power. So 5 times 1 is what this simplifies to. Similarly, I think this was supposed to be 3rd. Let's get rid of that. I think that was supposed to be 3rd power up here. Okay. Similarly, 5a to the 0, b to the 3rd. Here I have my 0. It's only on the base of a. So that a to the 0 can be replaced with a 1. So this becomes 5 times 1 times b to the 3rd, which is 5b to the 3rd. Okay? It's only that base to the 0 that can be replaced with a 1. So if we're looking at problem number 4, where's our base? Our base is all of 5y. This whole thing is our base. So the base to the 0 power becomes 1. See how much easier that is, right? I mean, I hope you see how much easier that is. Okay. So what about negative exponents? Now, negative exponents come about, again, because of that quotient rule. So if I had 5 to the 4th over, let's say, 5 to the 6th, right? If I'm using the quotient rule, this is 5 to the 4 minus 6, which is 5 to the negative 2, because it's always top minus bottom on that quotient rule. It's always top minus bottom. So I have to do 4 minus 6. Have to. So what does this mean? 5 to the negative second power doesn't tell me much of anything. But if I go back to the old school, 5 times 5 times 5 times 5 over 5 times 5 times 5 times 5 times 5 times 5, right? 5 to the 4th is 4 of them. 5 to the 6th is 6 of them. Look at what happens. 5 over 5 is 1. 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 And I end up with 1 over 5 squared. So what does this mean? 5 to the negative second is the same as 1 over 5 to the second. Or a base, I'm trying to figure out, to a negative power. Negative power is the reciprocal of that base. To the absolute value. Absolute value of that power. Okay. Oh man, that sounds confusing. But basically the idea is, if you have 5 to the negative second, this is the same as 1/5 to the second, or 1 over 5 squared, which is 1 over 25. Find the reciprocal, flip it. Okay? If I have -3 to the negative 4th, this is the same as a negative 1/3 to the 4th, which is a negative 1 to the 4th over a 3 to the 4th, or 1 over 81. Too good? Too bad. X to the negative 5th is the same as 1 over x to the 5th, or 1 to the 5th over x to the 5th, which is just going to be 1 over x to the 5th. 4y to the negative 3rd. Careful of where your base is. This negative 3 is only on the y. So this would be 4 times 1 over y. The reciprocal of y is 1 over y to the 3rd. So we will have 4 times 1 to the 3rd over y to the 3rd. Or 4 over y to the 3rd. Now, some of you are saying, okay, Amy, why isn't it 12? Where'd you get the 4? Well, 1 to the 3rd power is going to be 1 times 1 times 1. And 1 times 1 is always 1. So 1 raised to any power is always going to be 1. It's another nifty little thing that happens. So anything to the 0 power is 1. 1 raised to any power is 1. Lots of 1s. Okay. All right. use the negative, use the 0. Got it. All right, so we are going to look at goal 3, which means we're going to write some equivalent expressions using positive integers. Negative integers occur all the time, but we tend to rewrite them using positive integers. Why? Much like negative numbers or fractions, they're just not nice to work with. So we prefer to work with positive integers. So we're going to look at some strategies for rewriting negative exponents as positives and how that works with the reciprocal. All right? Okay, so here's what basically happens. If you have, let's say, an x to a negative exponent, let's say x to the negative fifth, right? One of the things you can remember is to use the reciprocal. This is the same as 1 over x to the fifth, which would be 1 to the fifth over x to the fifth. 1 to the fifth is 1 times 1 times 1 times 1 times 1, which is just going to be 1. And x to the fifth is x to the fifth, right? Notice, reciprocal. When I use the reciprocal, the negative goes away. This happens even when that's in the denominator. So let's say I had 1 over x to the negative third. This would be the same as the reciprocal of 1 over x to the negative third, which is just going to be x, the reciprocal, to the third. It's really a beautiful thing. The negative reciprocal flips top bottom. That's what it does. It does not change the sign of your answer. This was positive, it stays positive, right? If it was negative, it stays negative. But there are a few other strategies. One of them is just to keep working with the negative number. First, let's practice a few. I'm getting ahead of myself. All right. So if we have 1 over 4 to the negative third, this would be the same as 1 over 4 to the negative third. That negative power means I need the reciprocal of the base. The reciprocal is a flip of the fraction. So 1 over 4 flips to 4 over 1. Once I flipped it, I don't need the negative anymore. This is just a 3. So this would be 4 to the third over 1 to the third. 1 to the third is just 1. 4 to the third is 4 times 4. That's 16 times 4 again is 64. Notice this is not negative. It's still a positive number. A negative exponent does not change the sign on your answer. Okay? The negative exponent itself does not change your sign on your answer. Okay. What to do about number 10, where I have 4 squared d to the negative eighth? Well, I can do this long way, or I can recognize the pattern that a negative exponent in the denominator will make it positive in the numerator. So this would be the same as 4 squared times d to the eighth over 1. Over 1 doesn't do anything. So this would be 4 squared d to the eighth. And if you needed to, 16 d to the eighth. 4 squared is 4 times 4. That's 16. Okay. If I have 8 to the negative second over 5 to the negative third, the negative exponent means that I need to flip this from the numerator to the denominator. So this will be 8 squared. The negative exponent in the denominator means I need to flip it up to the numerator, 5 cubed. And once I flip them, I have no need for the negative. The negative basically indicates it's on the wrong side of that numerator-denominator fraction bar. Okay, so this would be 125 over 64. And that will not reduce any further. This is as far as I can go. All right. Taking a breath. Okay. Number 12 says r to the negative fourth over w to the negative sixth. I don't have a common base, so I can't do anything with those. The negative indicates that that r to the negative fourth is in the numerator, but needs to be in the denominator. So this will be r to the fourth. W to the negative 6, the negative in the negative exponent in the denominator indicates that it's in the incorrect place and needs to be in the numerator. So that negative will flip it up to the numerator, W to the 6th. I don't have the same bases, so this is as much as I can do. If we have number 13, which is a negative 3, B to the negative 2nd, important to note what your base is. The exponent is a negative 2. It is only on the B. It is not on the 3. So the negative 3 is in the correct placement. The negative 3 will stay in the numerator. B to the negative 2nd tells me that part needs to flip down into the denominator. So that would be B, and once flipped, there's no need for the negative anymore. It would be a negative 3 over B squared. And we're good to go. What about number 14? In number 14, it's important again to recognize that the exponent is negative 3 and the base is negative 5x. So all of this is your base, right? So all of that, which is currently in the numerator, because it would be over 1, needs to go into the denominator. So this would be a 1 over negative 5x, all of this to the third. And if I'm being asked to simplify this further, that's a 1. That would be a negative 5 to the third and an x to the third, which would be 1 over a negative 125 x to the third. If I'm going to write this algebraically in a more common usage, we would write it either as a negative 125 x to the third, or you will sometimes see it as a negative 1 over 125 x to the third. All three of these answers are technically acceptable. Normally, it is written as one of these two, though. Either that negative out in front saying, hey, the whole thing is negative, or that negative up by the 1 in the numerator. That's just common practice. It's not wrong if you do it the other way. Okay? All right, our next goal. Is to use all of our exponent rules in order to simplify a bunch of really weird looking expressions, okay? So here I've made a listing so that we can go over real quick, maybe not so quick, but so that we can go over the different, there's my black one, black marker, sorry. So we can go over the different algebraic examples. Okay, so for exponents, the property of an exponent of 1 says that if you have a to the first power, this is the same as just an a. That the exponent of 1 doesn't change the value of the number and it stays the same. The product property basically says if you have a to the m and you're multiplying that by a to the n. So if the bases are the same in your exponential expressions and they're being multiplied, that you can just simply add the exponents. The result of that multiplication will be the exact same base with the exponents added. Notice this is not 2a now. That's probably the biggest mistake. People think a to the m times a to the n is 2 a's to the m. No. It's just the exact same base. It's a, and a. Okay? The power of a power says if you have an exponential expression and it is taken to an additional power, what you can do to simplify this is multiply the powers together. This would be the same as that base to the m times n power. Okay? The power of a product, a to the m, b to the n, to the, I don't know, what did I use? P, I think I used. Here I have a product, powers, we're going to raise that to another power, is the power of the product. Power of a product is the product of the powers. That's how we usually say it. This would be a to the pm times b to the pn. we essentially distribute that outside power to any of the exponential expressions inside. All right. Second column, the property of zero says if you have an exponential base, or if you have an exponential expression where the base is raised to a zero power, this is the same as 1. Base to a zero power is 1. I should add that your base itself cannot be 0. 0 to the 0 power, not the same. But there's a whole bunch of stuff on 0 to the 0 power. All right, but any other base to the 0 power has to equal 1. The quotient property says if you have two exponential expressions where the bases are the same and they're being divided, the resulting quotient is that same base with the powers subtracted. Okay, the power of a quotient says if you have a to the m divided by b to the n, and you're taking this to another additional power, this is the same as the quotient of the powers. So this is the same as a to the qm over a to the qn. Oh, b, sorry, that's a b. Bases are not the same. If the bases were the same, we go right back to the quotient property. All right, and then lastly, we have negative exponents. If we have a to a negative m power, this is the same as 1 over a to the m. If you would like, this also means that if you have 1 over a to the negative n power, this is the same as a to the n. Right? What is our strategy? Our strategy in general is to follow all the rules. If you can think of this like almost like art. Oh, I'm going to get a little philosophical here. But if you can think of this almost like art, and we're trying to study a very specific type of art that has parameters and guidelines, and you can make all kinds of decisions within those as long as you stay within the parameters and guidelines. Okay? Now, that means that we can all make different and unique pictures of people as long as we have eyes, nose, mouth, face. There's a certain part that has to be recognizable. There are recognizable parts. Now, some of you, this is not going to be good. Some of you, this is too much leeway. So, when first beginning this, my strategy is to do this very similar to the order of operations. Go inside the parentheses first and see if there's anything that can be simplified and work your way out. Okay, so we're going to go from the inside and work our way out. That's going to be our general strategy from beginning. So I'm going to say inside out. And then I'm going to show you, there's a lot of rules here, right? There is a lot of rules here. So I'm going to show you my sort of shortcut / key that I used to do all the time when I was first learning this. So I would say, okay, here's the bases, and then here's the exponents. And maybe you'll see a pattern when I write this out. So when the bases are the same, and those bases are being multiplied. So I'm doing the product property now. When the bases are being multiplied, what happens to your exponents is that you add them. Okay? When those same bases are being divided, I'm talking now about the quotient property. So when those bases are being divided, the exponents themselves are subtracted. Okay? When you have the power of a power or the power of a quotient. So when you have the entire base taken to another power, and I'm going to use that chevron to indicate I've got something being taken to another power, what happens with the exponents? I multiply them. Right? These are the 3 main rules that I live by when I'm doing these. that if the bases are being multiplied, you can add the exponents. If the bases are being divided, you subtract the exponents. And if you've got some power already, if you've got some exponential power already, and you're taking it to another power, those exponents can be multiplied. Those are my three main rules, which then gives me, now I've got three main sort of cheats to remember. And that is that a to the first power is a to the 0 power is 1, and a to the negative m is 1 over a to the m, or flip it. Okay? These are the sort of 6 things that I would write down on my paper when I was trying to remember stuff, rather than writing out all these properties. Okay? Let's see how this goes. All right, switching back to my green, or blue, I guess I was using. We're going to simplify these expressions. Our strategy is to use these 6 rules and to work from the inside out. Those are our strategies. All right. We've got x to the negative second to the 8th. X to the negative second, I can rewrite as 1 over x to the second. That's using this a to the negative m is the same as 1 over a to the m. That's got to be to the 8th power. Now, I can use my power to a power here. This is going to be 1 to the 8th over x to the second to the 8th. 1 to any power is always going to be a 1. And here I have a power to a power. Means I can multiply those exponents. 2 times 8 is 16. Ta-da! Done. I only have positive exponents, so I'm good. Okay. Here we have m to the 4th over m to the 8th. If I work from the inside out, the bases are the same and they're being divided. So that means I can subtract the exponents. This will be m to the 4 minus 8 to the negative 5th. Inside out, 4 minus 8 is a negative 4 to a negative 5th. Now I have a power to a power. And according to the third rule I've got here, the power to a power, I can multiply those exponents. So this would be m, negative 4 times negative 5 is 20. Positive exponents, I'm good. Problem number 17. I have k to the negative 3rd times k to the 0, all of this to the negative 4th. Strategy is to work from the inside out. Is there anything inside the parentheses that I can simplify? Well, this would be k to the negative 3rd. K to the 0 is 1. Then I'm going to take this to the negative 4th. I have 2 choices here. I do see, and this is what I see, it's not necessarily what you will see each time out, but I do see that k to the negative 3rd times 1 would just be k to the negative 3rd. And then I can take it to the negative 4th. I see a power to a power, and I saw that first. So if I do negative 3 times negative 4, that's going to be k to the 12th. And that's a positive exponent, and I'm done. Okay. Now, is that the only way to do this problem? No. And if you don't want to know the other way, fast forward through this next bit. Okay. So the other way that you might do this problem is to write this as 1 over k to the 3rd times 1, because that's k to the 0 is 1, to the negative 4th. So that's going to give me 1 over k to the negative 3rd, or k to the 3rd, sorry, not negative, k to the 3rd to the negative 4th. The negative 4th says I need to flip this. So now that's going to be k to the 3rd to the 4th, which is still k to the 12th. Whew, same answer. Right? You could have also, this is why this is just a little bit crazy. You could have also gone, this is 1 to the negative 4th k over k to the negative 12th. But k to the negative 12th indicates that is in the wrong spot and needs to flip up into the numerator, which would give me k to the 12th. So they'll all get to k to the 12th if you're doing them correctly. But you need to find a patterning that works for you in terms of getting these right. And the only way you're going to do that is through practice. When there's creativity involved, and there is some creativity and multiple paths, one of the things you have to do is learn what works best for you. It's not so much about me telling you how to do it as you discovering on your own which manner or form works best for the way that you learn and for the way that you work through a problem. Okay? All right, let's try number 18. Here I have 15 a to the 7th, b to the 3rd, over 25 ab to the 10th. Well, I'm going to assume I'm going to keep a numerator and denominator right off the bat, at least to start with. Then I'm going to look first at the numbers. I have 15 and 25. 15 and 25 are both divisible, so divisible by 5. So I'm going to start by simplifying those. 5 goes into 15 3 times. 5 goes into 25 5 times. That keeps a numerator and a denominator. I then have a to the 7th over a. If I look at my next grouping, my bases are the same. I can use the quotient rule to do a to the 7 minus 1. That's going to be 6. And then I can look at the b's, and this will be b to the 3 minus 10. Remember, it's always top over bottom. This is going to give me 3/5 a to the 6th, b to the negative 7th. Where did the numerator and denominator go? They're still there. I've just sort of put the a to the 6th, b to the negative 7th in front. If I were splitting this, they would be up top like they were here. So if you are more comfortable writing this as 3/5 a to the 6th, b to the negative 7th, that's fine. You can keep it this way, all right? But this is the same. These are two formats of the same answer, just an FYI. Now, I cannot multiply the a and b together. They are not like bases. But I do have a negative exponent, and they want only positive exponents. So this negative exponent has to kick its base down to the denominator. Or if you'd rather, it's going to kick this base down to the denominator. So this is going to give me a 3a to the 6th. That was a positive exponent. It can stay right where it is. Over 5b to the 7th. And now that I've moved it from the numerator to the denominator, I don't need to put a negative on it anymore. All right? I think I've got some more. I do. Oh, I've got some fun ones here. Okay. Oh, look at number 19. Woo, boy. Okay, remember your strategies. And remember the shortcuts. Okay, where am I? Okay. I'm going to write it out here. So I've got the base and the exponents. If my bases are being multiplied, my exponents can be added. If my bases, like bases, are being divided, my exponents can be subtracted. If my exponents are taken to other exponents, power to a power, that's the chevron, my exponents can be divided. I need to remember the 3 other little shortcuts, which is that a to the first power is the same as a to the 0 power is a 1, and a to a negative m is 1 over a to the m. Okay, those are my 6 facts that help me get through exponents. All righty. Okay, here we go. Oh, second strategy, inside out. I'm going to start inside my parentheses and work my way out. So if I do that, then I recognize that this r over r here is a quotient. And I can start with a -3. R to the 4th and an R to the -3rd would be R to the 4 minus a -3. Minus a minus is still a plus. Just be careful about that. And I've got these guys here. I've got t to the -3rd over t to the 7th, which will give me t to the -3 minus 7. And that technically would be over a 1. All of this to the 3rd power. Okay, that's going to be a -3 r to the 7th, t to the -10th, all of that over 1 to the 3rd. I can't leave the denominator empty. I mean, I essentially took everything out of it when I did that quotient rule because there wasn't a number left down there. So I'm going to hold its spot with a 1. That's why I'm doing the 1. I got to hold the numerator denominator line. Okay, so, but I don't need the 1 anymore, do I? Oh, but I could. I've got t to the -10th, right, inside, and they want positive exponents. So I'm going to do this. I'm going to kick that t to the -10th down. So I've got a -3 r to the 7th over t to the 10th, all of this to the 3rd. Whew. Okay, so now this is the power of a quotient. So now I've got to take this power to a power and I can multiply them. So this guy is the same as -3 to the 3rd, r to the 3 times 7 over t to the 3 times 10. -3 to the 3rd is -3 times -3. It's a positive 9. Times a -3 again is a -27. R to the 3 times 7, which is 21, over t to the 30th. Here we go. One at a time from the inside out. Okay, I got an answer. Let's try number 20. For number 20, inside out is my scope here. So I've got a to the 3rd over a to the 2nd. That's going to be a to the 3 minus 2. I've got b to the -2nd over b squared. That's going to be b to the -2 minus 2. That takes away all my denominators, so I'm holding it over 1. Oop. And this is going to go to the -2 power. All right, this is going to give me a to the 1st, b to the -4th over 1. All of this to a -2nd. I do have a b to the -4th inside. That should get kicked down to the denominator. And once I move it to the denominator, a to the 1st over b to the 4th, it will be positive, but I'm still taking all of this to the -2nd. Power to a power means I can multiply. I'm going to go up this way. That's going to give me a to the 1 times the -2, which is a -2, over b to the 4 times the -2, which is -8. Now they're both negative again, which means they're in the wrong spots. So this is negative, meaning it's got to get kicked down to the denominator. And this is negative in the denominator, so it's going to get kicked up to the numerator. That's going to give me b to the 8th over a to the 2nd. And there we go. I have an answer there. Again, the bases are not the same, so I cannot condense this any further. This is as far as I can go. Right? Okay. Now, I'm going to be a little bit extra here. I just want to show you that these rules work no matter what is in the exponent spot. When you see something like 5 to the n, that means they have 5 written down a number of times. How many times? There are n of them, however many. We can treat that n, that variable, just like we would any other number that's there. For example, here we have 7 to the x power over 7 to the x power. It doesn't matter what that x value is. You have 7 to the x power. That's going to be some number over exactly 7 to the x power again. You have a number over itself. If I use the exponential rules, I will have 7, which is my base, to the x minus x power. If I have x and I take x away, that's 7 to the 0. That is still 1. It does make sense because even though I don't know what 7 to the x is, it's the same on top and bottom. It's got to be the same number. And any number over itself is going to give me 1. For number 22, I have 5 to the x power times 5 to the y power. The bases are the same. This is 5 to the x times 5 to the y. When the same bases are being multiplied, the exponents can be added. So this would be the same as 5 to the x plus y. It doesn't matter that I don't know what x and y are. I'm still using the same rules, and they are applying. So if x was 2 and y was 7, this would be 5 to the 9th. If x was negative 1 and y was 10, this would be 5 to the 9th. If x was 1/2 and y was 2/3, it would still work. This would be 5 to the 7/6. Okay? We're not doing fractions. We're not doing fractions and exponents. It was only an example. Please do not panic. Please do not panic. We're not doing fractions. This is as far as we're taking it. Okay? All right. So here I have x to the 3b times x to the 5b. You notice the bases are the same? If the bases are the same and they're being multiplied, the rule is that I can add the exponents. Bases are the same being multiplied, add the exponents. So this would be x to the 3b plus 5b. Can you simplify 3b and 5b? Yeah, this would be x to the 8b. Do I know what that is? No clue. No clue. I just know it follows the rule. I am following the rules. This is a perfectly fine answer. Okay? Similarly, I have y to the exponent of x plus 5 over y to the 5. Bases, same. When the bases are the same and they're being divided, the exponents can be subtracted. So this should be the same as y to the x plus 5 minus 5. Can you simplify x plus 5 minus 5? Well, the plus 5 minus 5 will zero out. This will be y to the x plus 0, which is just y to the x. Simplified using the exponential rules for algebra. You have an assignment to do in section 5.2. I think a couple of these are at the very end. But this is an FYI. I'm not going to test on them. All right? Okay, we will see you next time for 5.3. Thank you.